Okay, thank you. Yeah, good afternoon, everybody. And I'm going to now talk about this follow-up work from what Tamara has just spoken about. Again, talking about holographic duality between local Hamiltonians, but this time from random tensor networks. And again, this is joint work with Tamara and Toby that we did for my master's and into the first year of my PhD. So since there's quite a large overlap in the background from Tamara's talk, I'm just going to give a super quick recap of the context that we're in before going into more details about the setting that motivated this work. In particular, what are the features of ADS-CFTs that we might want to reproduce with toy models, and what are the successes and limitations of previous codes. And then in the second half, I'll talk through another toy model construction, describe it, and how we showed some of the properties. So very quick recap of ADS-CFT, the holographic principle, this idea that the description of a gravitational theory in the bulk of a space can be encoded at its border, using this sort of picture where we've got some quantum gravity in anti-de Sitter bulk spacetime, and on the boundary we've got a conformal field theory with some ADS-CFT dictionary that takes us between the two theories. And again, if we've got a 2D bulk and a 1D boundary, we can think of this sort of cylindrical picture with time going up the z-axis. And dualities are useful and interesting because problems in one setting might be easier solved by first mapping into the dual. So for example, in ADS-CFT, this has been used to study strongly interacting conformal field theories by mapping semi-classical gravity in the bulk. And it's also hoped that you can gain some insight into theories of quantum gravity by using it in the other direction. But as Tamara said, we don't really know what this ADS-CFT dictionary looks like in terms of a complete mathematical description. So we have to rely on these partial toy models. And the ones we're talking about are in the form of holographic quantum error correcting codes built up of tensor networks. Again, how this works is in embedding a tensor network into our anti-de Sitter bulk, leaving some legs uncontracted, which we then associate with bulk degrees of freedom, cutting off our tensor network at some finite radius, and then associating the dangling indices of these tensors with boundary degrees of freedom. And in this way, our tensor network is then describing a map from one space to the other. So there's been lots of previous works that have constructed different types of holographic quantum error correcting codes. None capture all of ADS-CFT, but different features of the duality have been reproduced to various extents. So in order to motivate where our work sits in all of this, I'm going to go through 3 ways, among many others, that a successful toy model might aim to replicate holographic duality. So starting with the focus of the work that Tamara just presented is a mapping between models. So we want a model in the bulk to be dual to a model on the boundary. And when we're thinking about tensor network toy models, the thing we want is for local bulk operators and local Hamiltonians in the bulk to be mapped to local boundary operators and local boundary Hamiltonians. And this isn't always the case. And you might have some local bulk operator near the center of the bulk that requires a large global interaction on the boundary, which is bad. And once we have this locality, we might also then look for the boundary to be Lorentz invariant or ideally a quantum CFT. A second feature of ADS-CFT is this link to error correcting like properties, which we're going to think of in terms of complementary recovery. So again, as Tamara has gone through, if we've got a local bulk operator, then the information of this operator is encoded with some redundancy and secrecy on the boundary, which means it can be reconstructed on multiple different portions of the boundary and protected against different erasures. So this operator X can be reconstructed on B or A, but not on B complement or the complement of A. And this makes sense through the no cloning principle. And this error correcting property can be summarized as complementary recovery, which states that if you've got any bulk, local bulk operator, and you split the boundary into two, that bulk operator can be either recovered from one of the boundary sections or the other, but never both. And then the final feature that we're going to consider is the entanglement structure of ADS-CFT. As Tamara said, there's this link between entanglement and geometry, which is described by the Ryu-Takayanagi entropy formula. So this states that if you take the entropy of some state on the boundary that's supported on region A, then this should be proportional to the area of the minimal geodesic that cuts through the bulk. And this has quantum corrections, but it should be correct up to leading order for any boundary subregion A. Okay, so then thinking about how we relate this entropy formula to tensor network models. So a picture of the happy code from the happy paper. We've got our boundary subregion A, and we want to in some way reproduce the Ryu-Takayanagi formula where we're proportional to this area. So we're going to translate the minimal geodesic through the bulk with the minimal cut through the network, where we're measuring the length of the cut by how many tensor legs it's crossing. And the happy code describes the greedy algorithm, which is a way of trying to find the minimal cut in the network. And we describe the output of this algorithm as gamma A star. And the idea of this is that it tries to find the minimal cut by locally checking whether by moving to include or disclude a tensor, whether this is going to reduce the length of the cut. And yeah, just iterates starting from being anchored at A until it finds a local minimum. So the entanglement structure of the happy code does echo ADS-CFT in that there is some sort of relation. But here's a quick summary of some of the different cases and to what extent the Ryu-Takayanagi entropy formula is satisfied in each. So at the first step, if you consider a tensor network where we have no uncontracted bulk indices, which corresponds to not having any bulk degrees of freedom and just having some holographic state on the boundary, and we consider A being connected boundary region. So in this restricted case, you do get the Ryu-Takayanagi entropy formula being obeyed exactly, which they show using the greedy algorithm. Taking it one step further, we're still considering A being a connected boundary region, but now including letting there be uncontracted tensor indices in the bulk again. And for example, applying a product bulk state. In this case, then we no longer have exact Ryu-Takayanagi. Instead, we just have these bounds on the entropy of our state that's supported on A. So the upper bound is just true in general for all tensor networks. And then they show this lower bound in the happy paper, where gamma A star is the output of the greedy algorithm starting anchoring at A, and then gamma AC star is the greedy algorithm starting anchored on the complement of A. And if the algorithm worked perfectly, you'd hope that they would both get to the same cut through the network, but this is sort of implying that sometimes it doesn't, and it doesn't sometimes where you have uncontracted bulk indices. And in this case, this lower bound is lower bounded by the number of tensor legs that are crossed by both of these outputs. So if we have both of these lines not being equal or having some residual region in the middle, the size of this residual region is going to determine how tight this lower bound is and how close to the Ryu-Takayanagi we have in this case. Going again further, if we're saying that we now want some entanglement in our bulk state, or if we want the boundary region to be disconnected, so considering A being 2 or 3 disconnected regions, these proof techniques fail, so they aren't able to say how the happy code is mirroring ADS-CFT in this way. Okay, so moving on to thinking about types of tensor, as the hint is going to be moving from perfect to random. So the type of tensor that we're going to build the network from is clearly going to dictate properties of the model we end up having at the end. So here are some of the options we could choose. where if we're having a tensor here, T, that's got little t legs, and each leg has got dimension P, this describes a state like this. And in this way, we can use our state that the tensor describes, where all the legs are uncontracted, to define the tensor, where here, this is the components of the tensor. So in the first case, which is what they use in the happy code and in the extension Tamara just presented, they choose perfect tensors, where psi is an absolutely maximally entangled state. So A and E states are the ones where if you take a bipartition, you've got maximum entropy on the reduced density matrix of that partition. And they also just give isometries as Tamara described. But we might also want to choose random tensors, which are just, again, described by random states. And a way we could generate random states is starting with some reference state, for example, the vacuum state, and then applying a random unitary to it. And another choice could be random stabilizer tensors, where we start with a stabilizer reference state. Again, the vacuum state will do, and apply a random Clifford element to it. And it's, well, Tamara's gone through, and it seems quite clear why perfect tensors could be a good choice, because they're by definition isometries, but potentially not quite as clear why we'd expect models made from random tensors to have any to be a good choice. But we would expect high dimensional random tensors to show similar properties to perfect tensors because of measure concentration. So measure concentration, the recap is the idea that if you've got a smoothly varying random function on the hypersphere, that's going to concentrate about its expectation as the dimension of the hypersphere grows. And this is formalized by Levy's lemma, where the smoothly varying function is encapsulated in the Lipschitz constant of the function appearing in the bottom here. And then if I've got a function of a random state and I choose, evaluate the function at random, the deviation of this function from its mean, being large, is going to decrease exponentially as I increase the dimension of the hypersphere. And the way we would apply this to random states is if we note that the entropy of a random state is close to maximal, and we've got d-dimensional quantum states. These can be represented on 2D minus 1 dimensional hyperspheres. We could then consider our function being entropy, noting that the average of the entropy is close to maximal. This would lead us to conclude that we'd expect, as we take the dimension high, our random states are going to be close to absolutely maximally entangled states, and therefore our random tensors are going to sort of behave like perfect tensors. Then we also discussed what we might want to choose random stabilizer tensors, and that previous thing was true for Haar random states. So we generated the random stabilizer tensors by instead applying a random element of the Clifford group, and the Clifford group on qubits and QDIPs is a unitary 2 design if the QDIPs are prime dimension. And again, here's a recap of what a unitary 2 design means. Essentially, that if you're taking an average over second moments of 2 designs, this is equivalent to taking the average over the full Haar measure. And so if we were going to deal with random stabilizers, we'll need to use this 2 design property when considering averages of the network. So now, after that background, we're in a position to motivate this work by looking at 3 previous toy models that our work is going to build upon. So firstly, the happy code, which Tamara introduced. This uses perfect stabilizer tensors on qubits and places them in pentagons that tessellate a 2D hyperbolic bulk. And the main technique used in this paper is just the properties of the perfect tensors themselves, the fact that they're isometries. And then Tamara's just been through an extension of the happy code where they use perfect stabilizer tensors, this time on QDIPs, and increasing the bulk geometry to 3D, taking care to tessellate it in a way that they can learn things from and understand properly, able to add Hamiltonian simulation on top of these properties of perfect tensors. A different approach is taken in this 2016 paper by Hayden and others, which demonstrated that random tensor networks had also some properties of holographic duality. So they're using random tensors on high dimensional qubits, and in general an unconstrained graph structure. And the main technique of this paper was to use this mapping to the classical Ising model in order to show that these tensor networks also have properties of holographic duality. So how do these three different previous codes perform in terms of the three desired properties that we wanted from a toy model of ABS-CFT? So as Tamara has gone through, the happy code in general will have global boundary operators and global, so they're not able to map local Hamiltonians to local Hamiltonians. Although it does show complementary recovery, except in very few cases. So there are some places in the bulk where you could choose a local boundary operator and choose some pathogenic bipartition of the boundary such that the local bulk operator isn't recoverable in either. And yeah, I've gone through in what ways the happy code reproduces the Ryu-Takayanagi formula, but essentially only in very special cases. And we want to be able to have uncontracted bulk indices and consider different bulk input states. And Tamara's just been through how by the addition of Hamiltonian simulation, they were able to improve on the happy paper and generate local boundary operators. But then, how does the random tensor code go? So like with the happy paper, the output of the tensor network is going to be have large non-local terms. So in this way, not being able to map local Hamiltonians to local Hamiltonians and not being a map between models. However, using this other technique, they're able to show complementary recovery. And most importantly for this work, they had really good entanglement structure properties. So able to show the Ryu-Takayanagi formula in general for boundary regions, so including disjoint regions and considering what happens when you have entanglement in the bulk, etc. So leading us to the main aim of this work, so looking at these three, the idea was to apply the Hamiltonian simulation techniques, but instead to a tensor network built of random tensors in order to sort of hopefully inherit all of the good properties of these three codes and demonstrate these properties simultaneously. Okay, so that's all the motivation done, hopefully. And now moving on to how this toy model works, describing it and then going through some of its properties. Okay, so again, this toy model is a sequence of simulations with respect to the definition laid out in Toby and Ashley's Stephen's earlier paper, where we're encoding a local Hamiltonian in the bulk to something on the boundary. And the first step is to apply the tensor network encoding, where we can have a 2D or a 3D bulk, which is tessellated again by Cox dipolotopes. So we're inheriting all of the geometry and structure that Tamara and Toby worked out in their earlier paper. Again, just to remember how gross those pictures looked. Yeah, and this, after applying this tensor network encoding, we've gone from a local Hamiltonian on bulk qubits to a highly non-local Hamiltonian on our boundary qubits. And then, as you probably expect, the second step of the simulation is to apply these Hamiltonian simulation techniques. And Tamara's gone through, this allows us to simulate the physics of this highly non-local Hamiltonian in the low energy subspace of a local Hamiltonian. In the 2D boundary case, we're able to apply a similar sequence of perturbation gadgets as in the work that Tamara's just presented. And in the 1D boundary case, again, using the history state method from the paper she touched on. And this lets us go from highly non-local Hamiltonians on boundary qubits to a local Hamiltonian on a new set of boundary qubits. And just in Tamara's earlier work, the reverse direction map is also defined. So it's got a bidirectional duality. And this completes the description of the construction. So now to go into some more details to give some insight into why it wasn't immediately obvious that we could just swap the perfect tensors for random stabilizer tensors and just inherit all of the properties. So firstly, why did we have to go through the effort of choosing random stabilizer tensors? Would have been probably a lot easier to not go through the effort of using two designs and just have the half measure. So as Tamara touched on this briefly in her talk, but stabilizer tensors are essential for the second step because we need to preserve the Pauli rank of operators. We're taking this non-local Hamiltonian on n boundary qubits, and we're ending up with a local Hamiltonian that's going to act on a different set of boundary qubits. And it's important to know how these how this is going to scale with the original set in order to know whether the Hamiltonian we're describing can actually live on the boundary as we think of it of the tensor network, or whether we've added loads and loads of ancillars and it's needs to be a lot bigger now. So yeah, we needed to make sure we had this stabilizer property so that the Pauli rank was preserved and we could just inherit this good scaling in terms of polylog of the boundary qubits. And then once we've been forced into using stabilizers, there's another advantage, because as we've gone through using measured concentration, we know that high dimensional random tensors are close to perfect with high probability. But since we have the structure of the stabilizer group, we know that stabilizer states have quantized entropy. So we can actually bound the probability of high dimensional random stabilizers being exactly perfect just by making the deviation smaller than the quantization unit. And then this is all useful since with high probability, we have exactly the same setup as in the work that Tamara described earlier. So all of that work using like the tensors being isometries and describing maximal distance code can all just be directly recycled with high probability. So this concept that random stabilizer tensors being equal to perfect tensors going to 1 as the tensor bond dimension increased was already known from previous work. But we needed to know how the scaling went precisely with P, I'm gonna call the tensor bond dimension P, and the number of tensors in the network. For this second step with the Hamiltonian simulation. So just a few more slides on how we showed the scaling. So given a random stabilizer tensor with T legs, each with dimension P, we first found the probability that the entropy of the reduced state on equal bipartition is not maximal. And we do this using by bounding tails of two designs, getting this 1 over P to the B, where B is something strictly less than 1. And if our probability of not being equal is vanishing as we're increasing P, then it makes sense that the probability of the state being maximally entangled across a given equal bipartition is going to be going to 1 as we increase P. However, there are more than one distinct way to equally bipartition the tensor. We need it to be maximally entangled over all of these bipartitions in order for the tensor to be perfect, since we're going to be using each tensor with a different combination of input and output legs, depending on where it is in the network. So making no assumption about the dependence of the events, Fresher inequalities bound the conjunction probability. So if I have n events and I want to bound the probability of them all happening at the same time, this can be lower bounded by the sum of the individual probabilities taking minus the number of events I have. So using this inequality along with the probability from the earlier slide, this gives us the joint probability of all bipartitions satisfying the entropy being maximal. And this is again bounded by here, where you can see that if I take P large, that's going to go to 1. So with high probability, we're going to have all of our, all of the bipartitions maximal, and the tensor is going to be perfect. However, for the network to be in isometry, we need this to be true for all of the n tensors, which are chosen independently in the network. So we're now having to raise this to the power n. So our dimension P, in order to keep the probability high, is going to have to depend on how the size of our network, which is something new that wasn't previously in Tamara's original paper, which is kind of annoying. But for any size network, we can always choose P large enough that this probability is going to be high. Okay, so the outcome of all of that is if we take P large enough, then the network is an exact isometry with high probability that's going to go to 1. And the error correcting properties and the way that they use the Hamiltonian simulation techniques can all just follow. But the main expected advantage of constructing our network from random tensors was that we'd want to inherit this good entanglement structure that was shown in this 2016 paper. So without going into much detail at all, just quickly how in this work they showed that random tensor networks satisfy the Ryu-Takayanagi formula, where A is any boundary region, including disconnected regions. And the way they do this, as I kind of mentioned earlier, is that they interpret functions of the network as partition functions of the classical Ising model. And the way this works is then as we take the dimension of the bond dimension high, this is akin to going into the low temperature regime in the classical Ising model, where the partition function is dominated by the ground state. And we know what the ground state of the Ising model is. It's the thin configuration where the domain walls are minimized. So in this scenario, the Ryu-Takayanagi surfaces manifest as spin domain walls. And the main advantage of this technique is we can apply it to connected and disconnected regions, and also having uncontracted bulk indices. So loosely speaking, associating a spin with each tensor in the network and each having a pinning field each of the dangling legs, the domain walls are minimized for the ground state, and this corresponds to the entropy of the state on A being proportional to the Ryu-Takayanagi surface. So using this method with random stabilized tensors, but in Cox politopes, just to see how this would go through. So it was immediate that if we have bulk stabilizer states, the Ising mapping gives the Ryu-Takayanagi formula for general boundary regions, which is good, but we might not want to restrict ourselves to stabilizer states. So in order to get a more general result, we had to bootstrap via complementary recovery. Since complementary recovery would imply, considering it can only be reconstructed on one, not the other, that no local operator in the bulk can change the entropy of two boundary subregions. So if we have complementary recovery, this means we can apply local operators in the bulk to get from bulk stabilizer states to general bulk product states without changing the entropy, and hence without changing the satisfaction of the Ryu-Takayanagi entropy formula. So looking at the limiting case, we could see that if we place an extra constraint on the Cox politopes that they have to be odd-faced, then this Ising mapping technique gives complementary recovery for all bulk positions and boundary part partitions. So removing the pathogenic regions that you could choose if you, not having any pathogenic regions, and it being true in general. So since we now have complementary recovery, we're allowed to apply local operators and see that the Ryu-Takayanagi formula is going to apply in general for bulk product states. So in summary of what the entanglement structure for this code is, if you've got random stabilized tensor networks with odd-faced Cox tessellations, this leads to the Ryu-Takayanagi entropy formula holding for in general boundary regions that could be disconnected, with expected corrections in the presence of bulk entanglement, which they go through in the original work, and that should all follow. And again, we have complementary recovery for all bulk positions and boundary bipartitions with no exceptions. And these are both improvements over perfect codes. So just to summarize our main results in these four key properties of our construction, considering both steps satisfy the simulation theory, we can say that all relevant physics of the bulk Hamiltonian are going to be arbitrarily well approximated by the boundary Hamiltonian, where these errors are tracked, and we're able to make them arbitrarily small just by tuning parameters in the construction. And again, by all relevant physics, this includes things like the eigenvalue spectrum of the Hamiltonian, partition function, and the time dynamics. So all of that work, thinking about time dynamics and energy scales that Tamara went through, should also be true in this model. Secondly, considering we have that Hamiltonian simulation step on top of the tensor network, our boundary Hamiltonian is going to be too local and acts on nearest neighbor boundary qubits, realizing a mapping between models in this sense. Thirdly, any local bulk observable will have a set of corresponding boundary observables that act on portions of the boundary, as described by the ADS Riddler reconstruction, giving complementary recovery. And finally, the entanglement structure does mirror ADS-CFT, as the Ryu-Takayanagi entropy formula is obeyed exactly for any boundary subregion in the absence of bulk entanglement. So just to conclude, the techniques from these previous holographic error correcting codes could be successfully employed together with no arising contradictions, which gave a more complete toy model of holography, which can be summarized by this table. So by using random stabilizer tensors on high dimensional qubits, if we have a 2D or 3D bulk tessellated by Cox volotopes, and again, like Tamara said, the perturbation gadgets generalize to higher dimensions, and the only thing would be to check that there exists a Cox to holotope tessellation which has odd faces. And in this setup, we're able to apply the techniques of Hamiltonian simulation and mapping to classical Eisenmodel in order to achieve these three features of ADS-CFT simultaneously. So local boundary operators, complementary recovery, and the Ryu-Takayanagi formula. Again, this is just like one further step, and it's far from a complete model of ADS-CFT. For example, the Hamiltonian is still not Lorentz invariant, still not conformal field theory-like. But another direction to take this would be to use these toy models to test claims in holography. So if there's something we know to be true in ADS-CFT, are we able to get the same result using these toy models? And if not, why is that indicating that we need to include gravity, or that we need to just improve the models in some other way? Yeah, and these are the references that I've been referring to during the talk. So yeah, but that brings me to the end of what I've got prepared. So thank you for your attention. I hope you found it somewhat interesting.